Hello and welcome back to PC Retro Programmer. In the past few videos in the CGA graphics series, we've been drawing lines and circles on the screen, but it's high time that we did some code optimization and push these as fast as we can. But before we do that, we need to know how fast the current code is going, and for that we're going to need a timer. So in today's video, we're actually going to write a fairly straightforward timer based on the programmable interval timer of the PC. In fact, we're actually going to intercept a DOS interrupt which is triggered by the programmable interval timer. Now the programmable interval timer, or PIT for short, is the 8253 chip in the PC, and it runs at 1.193182 MHz. That's a quarter of the clock frequency of the CPU, and this is no accident. They both run off the same clock oscillator. Now, the way it works is that there are three counters inside the PIT. There's a channel 0, channel 1, and a channel 2 counter. And these count down at this frequency. And when they count all the way down, an action is triggered. So for example, in the case of the channel 2 counter, this is used to drive the PC speaker. The channel 1 counter is used for periodic dynamic RAM refresh. And it's the channel 0 counter that DOS uses for its system timer. And it sets things up so that it gets a pulse 18.2 times per second approximately. So what DOS does is it puts the maximum possible value in the channel 0 counter. You might imagine that being a 16-bit value, that's FFFF in hexadecimal, which would be 65,535. But the way it's set up, you can actually count one more than this if you put the value 0 in the counter. And that's then 65,536. And if you divide this frequency by 65,536, you get 18.20648 Hertz and some change. And what happens is on channel 0 of the PIT, every time it counts down to 0, it triggers an interrupt along interrupt request line 0, and that triggers interrupt 8. Now whenever the CPU gets an interrupt, it looks in the interrupt vector table at the very beginning of memory, and there are slots for each of the interrupts, and these are basically pointers to routines in memory that are going to handle those interrupts. So in the slot for interrupt 8, there's an interrupt vector, basically a pointer, to an interrupt handler, a routine that DOS actually installs to intercept these pulses that are coming in approximately 18.2 times a second. And it uses that handler, which is triggered that often, to update the system time. But the other thing that DOS does with this is it triggers interrupt 1CH, and this is actually designed for us to intercept so that we'll get a pulse 18.2 times a second approximately. So what we're going to do today is write our own interrupt handler to intercept interrupt 1CH, which is what it's designed for, and we're going to use the ticks that are coming in at this frequency, and we'll count those in order to time our code that we're trying to profile. So let's take a look at the code that I wrote for this. I've unimaginatively called this timer.asm. And we're going to need a few functions to make all of this work. The first of these is obviously the interrupt handler itself that we have to provide. And it has a particularly simple job. It's going to fire 18.2 times per second, basically every time DOS triggers interrupt 1CH. And all it needs to do is to increment a counter every time it gets called. So that counter is this ticks variable, and I've made that 16 bits so that we can count quite a few ticks. But I'm actually not going to count every tick. We're only going to count when the timer is currently on, and that'll be indicated by this variable here. It's just a byte which will be either 0 or 1 to indicate whether the timer is currently on. So if it's a 0, the interrupt handler will know that it's not supposed to be counting ticks at the moment, so basically it will do nothing when it's called. But if this is a 1, the interrupt handler will know that it's supposed to count the ticks, and so it'll increment this ticks variable every time it gets called. Now we'll need a couple of other functions. We need one to install our handler in place of the one that's currently dealing with interrupt1ch, and another one to uninstall our handler and restore it back to the original handler. So of course we need to store the vector for the old handler somewhere, so we need a variable that can store a far pointer, and these vectors are 4 bytes each. There's 2 bytes for an offset address and 2 bytes for a segment address. So a far pointer basically consists of an offset and a segment. And so we need 2 words for that, and that's what the DD is about here, declare double word. So that's where we'll store the old offset from the interrupt vector table for interrupt1c, and we'll put ours in instead. So let's take a look at the function that actually does that. First of all, we're going to be modifying the interrupt vector table, and we don't want interrupts on at the time, because if we'd half modified the interrupt vector for interrupt1c, for example, if we'd just modified the offset and hadn't got to modifying the segment yet, and then interrupt1c fired, it would have an invalid vector in the table. And so it would jump off to some bizarre location in memory and all hell would break loose. So we turn interrupts off so that that can't happen. And now we're ready to access the interrupt vector table. This is at segment 0, it's right at the beginning of memory. And we'll use the ES segment register for this. So we put 0 in the ES register. And now we can access the table. So we need the offset within the table for the vector corresponding to interrupt1ch, and as I said, each of these vectors is 4 bytes, so the offset is actually 4 times 1ch, and it's stored with the offset first and then 2 bytes later the segment. So we put those just into registers for now, and then we can put our vector in, the far pointer to our handler routine, which is our timer interrupt function. So we take the offset of that function and we put it in the offset location for interrupt1ch in the vector table. And what is the segment address that we're going to need? Well, of course, it's our code segment. So that'll be in the CS register at the moment. So we put that into the segment part of the vector. And so now we have the new vector pointing to our interrupt handler routine. So we've only stored the old vector in registers at the moment, so let's put it into our old timer handler variable in memory, which is what that was for. So now we have the old vector saved, so it can be restored later. And that's basically it. Now we turn interrupts back on again, and from that point on, our handler routine is called instead of the old one. And then, of course, we just return from our function. Now, the unhook timer basically does the opposite. It puts the old handler back into the vector table. So it turns interrupts off, and then we take the old timer handler vector, which we've stored in our variable, and we put it into registers, and then we set up the segment for the vector table, so segment 0. And then we reinsert that old vector back in the table. First the offset and then the segment address for the old vector. And that's basically it. Turn the interrupts back on and return. And that brings us down to our interrupt handler itself, which should be a very short piece of code. After all, it's going to interrupt running code, most likely our program, so we want it to take as few CPU cycles as possible. Now, the first thing that our handler needs to do is to call the old handler. And the reason for that is that we have no idea what that old handler was doing. It could have been set up by a terminate and stay resident program, for example. And unless we chain our handler to it, it won't get its timing pulses anymore, and it might stop operating. So, of course, we can't call that old handler anymore by raising an interrupt. After all, we've modified the interrupt vector table to point to our handler instead. So we actually have to call that old handler manually by treating it like a function and use the call instruction. Now, what is the address of that old handler? Well, we actually saved that out of the interrupt vector table into our variable old timer handler. So we actually need to call the address that's stored in our old timer handler variable. Now remember, this is a far pointer. It consists of an offset address and a segment address because that old handler could be anywhere in memory. And to tell it that we're calling a far pointer, we use this dword PTR here. Dword for double word, and this tells it that it's going to expect to find a double word inside this variable. So that's how we call the old routine, but this call is not actually going to do exactly the right thing. The problem is that when an interrupt is normally raised, the flags are automatically pushed on the stack. And call doesn't do that. So we actually need to manually emulate that by pushing the flags ourselves using a pushf. Now this is really important because when that old handler finishes, it's not going to return using a ret instruction. It's an interrupt handler. It'll return using an iret instruction. And the last thing that that does is to pop the flags. So we'd have an unmatched pop of the flags if we didn't push them here. So you'll often see this pushf call combination to emulate what happens when an interrupt fires. So now that we've called the old handler, we can do the tasks that our handler is supposed to do, and that includes checking whether the timer is on or not by looking at the timer on variable. And if it is on, it has to increment the ticks variable. And if it's not on, it should jump all the way down to here immediately and do nothing and just return straight away. Now notice that we're also using an iret because we're an interrupt handler, not a normal function. And you might also have noticed that I'm accessing our variables with this CS override. So there are three places where this is happening here for each of the variables that I access. And this is because I put those variables in our code segment, not in our data segment. So why did I do that? Well, it turns out we know nothing about the conditions when our interrupt handler gets called. In general, interrupts can happen at any time. And so you really don't know what was running at the time the interrupt occurred. Under normal circumstances, the CPU spends most of its time executing our program, and so most likely our code was running at the time. But it need not be the case. The CPU could, for example, be executing some other interrupt handler. It turns out that interrupts can actually interrupt other interrupts. And in this particular case, we know for sure that our code wasn't running because interrupt 1ch is actually triggered by DOS inside its interrupt 8 handler. So that's what was running at the time when this interrupt was called. So we're really going to not be able to rely at all on what is in the DS register. It'll most likely be something related to DOS. So that means that we can't access our variables in our data segment very easily. Now you can do it. You can load up the DS register with our data segment using the @data directive as normal, but that's going to make our interrupt handler a bit longer. Not only would we have to do that, but we'd also have to preserve the contents of the DS register using a push and a pop. And any other registers that we modify would also need to be saved. And so this thing would actually end up being quite a bit longer. So this is why it's more convenient to access variables in our code segment instead. Now, the thing is, the variables in our code segment we can access because we know that the CS register is set correctly for our code segment. Why do we know that? Well, we're actually currently executing our interrupt handler, and that's in our code segment. And it got there via the interrupt vector that we put in the interrupt vector table. We know that we put our code segment in for the segment address of that vector. So we do know that CS is actually set correctly for our code segment, and so that's why it's easier to access our variables in our code segment inside an interrupt handler. So if you look above, you'll see that all three of the variables that I declared, I did so inside the code segment. The assembler is absolutely fine with this. It's a perfectly normal thing to do. They're not in the data segment. So that's all that our interrupt handler needs to do, but there are a few other things that interrupt handlers often do, and I'll just discuss those briefly here. So first of all, if we were handling a hardware interrupt, for example, if we were handling interrupt 8 directly ourselves, then we need to acknowledge the end of the interrupt because the programmable interrupt controller is involved. Interrupt 8 comes in because of a signal along interrupt request line 0, and that's why the programmable interrupt controller would be involved. So to acknowledge the end of an interrupt, to keep the PIC happy, you have to put 20 in hexadecimal out to port 20, and so you'll often see that just before the IRAT in a normal interrupt handler routine. Now we don't need to do that here because we're not handling a hardware interrupt, we're handling the DOS interrupt 1CH, which is triggered by DOS itself from DOS's interrupt 8 handler. So actually here, DOS is responsible for acknowledging the PIC when it's finished with its interrupt 8 handler. Now the other thing you'll often see in interrupt handler is a lot of pushing and popping of registers. Unlike a normal function, an interrupt handler needs to preserve all registers that it touches. Now fortunately in our case we don't modify any registers, so there's no pushing and popping for that here. And the other thing you'll often see in interrupt handlers is that the interrupt flag might be turned on or off. Depending on what you want to do inside your interrupt handler, you might actually want interrupts to be on, and sometimes they're switched off inside an interrupt handler. So you may need to turn them on in order to do whatever it is you're wanting to do. So I'm not going to go into all of the details of that here, but look out for that in other interrupt handlers. So that's the end of our interrupt handler. So let's now look at the code for turning our timer on and off. That's this timer start and timer stop function here. Now these functions are particularly straightforward. This timer start just resets the counter to 0 and then puts a 1 in this timer on flag to indicate to the interrupt handler that it should be counting ticks. And likewise, timer stop just puts a 0 in that same flag to tell it to stop counting. But we should think about whether there could be a bad interaction here. What would happen if one of these pit pulses occurred between these two lines here? That would trigger an interrupt 8, and that would in turn trigger an interrupt 1CH, which would call our interrupt handler. And we're modifying variables here that our interrupt handler actually reads. So what could go wrong? Well, first of all, we don't need to worry about the interrupt handler running in the middle of an instruction. It seems that the CPU finishes executing the current instruction before running an interrupt handler. And we do have to note that there are two instructions here. This CS override is actually technically a separate instruction, and I don't think that's going to be an issue here. But we could still have the interrupt handler running between these two lines here. But I don't see any issues with that. If the timer was on and we reset the ticks to 0, then this is just going to start counting from 0, and that's exactly what we wanted it to do anyway. And most likely the timer is actually off at this point anyway. And if the timer is off, well, it's not going to be counting anyway, so it doesn't really matter if the ticks counter gets reset to 0. So in both cases I don't see any issues. But if we were worried about that, we could bracket this code with a CLI and STI so that interrupts were off while these two lines ran. And so that's something to think about when modifying variables that are accessed by an interrupt handler. Down here we only have one line anyway, and I don't see any issues here either. So now let's move on to our print hex function, which we use for printing a hex value to the screen when we output the value from our timer counter. This will be run from our main program, of course, and so we're just going to assume that the value we want to print is in the AX register. So it'll be 16 bits, and so that means 4 hexadecimal digits that we need to print. So we do a loop with a loop counter of 4, one for each of the digits. And the first digit we want to print is the leftmost digit, and that's actually corresponding to the upper 4 bits of AX. So to make those easier to get at, we rotate them around into the lower 4 bits, just using 4 1-bit rotates of the whole register. So now we're ready to copy that out into another register so we can turn it into a character value. We're going to need the ASCII value of the character that we want to print on the screen corresponding to that digit. So we copy it out into the DL register, and we'll AND it with OF just so that we've got the 4 bits that we're interested in corresponding to our value from 0 through 15. And to turn that into a character, the first thing we can do is add the ASCII value for the character 0 to the value. Now that means that if the value is between 0 and 9, then we'll actually end up with the correct ASCII value for the digit that we want to print. Now notice that we're not adding the value 0 to DL here, we're adding the character 0. So the assembler will turn this character here into the ASCII value for that character, and so that's what we're adding to DL here. All of the digits 0 through 9 are consecutive in the ASCII table, and so just adding that to a value 0 to 9 will give us the character that we want. But what about the other digits? A hexadecimal can also have digits A through F. Those correspond to the values 10 through 15. And they are not immediately after the digits in the ASCII table. But fortunately they're just 7 characters later in the table, so all we really need to do is add 7 in that case. So first of all, we check if we're below or equal to the digit 9, and if we are, well, everything's fine already. But if not, then we just need to add that 7 to the value, and then that gives us the correct ASCII value for the character that we need to print. So now we're ready to actually print this to the screen using the DOS print character function, which is function 2 of the DOS interrupt. And this expects that the ASCII value of the character we want to print is in the DL register, and fortunately that's exactly where it is already, so we don't need to move anything around. And notice that we're going to mess up the AH register, and we don't want to do that, so we just save AX into the BX register temporarily, because AX still contains the other digits we haven't printed yet. Then we call our DOS print character function, and then restore our AX back from the BX register, and that's really all there is to it to print a digit. So now we just need to loop around to print the other digits, so it'll loop back to our label up here, digit loop, and this is just going to rotate the next 4 bits around into the bottom of AX and deal with them in exactly the same way. So this will all get run 4 times, and that's the end of the function. So pretty straightforward to print a hex value on the screen, as you can see. Decimal is a little bit more tricky, and we'll cover that in a different video. So now we're on to our main program. It just starts by setting up our data segment. It sets up our interrupt handler, it starts the timer, and this is where we'd normally put the code that we're trying to time, but just to make this a simple program, I'm just going to wait for a key press, and then we'll stop the timer once the key has been pressed, and then we'll print the count to the screen. So of course the timer has been updating this counter ticks. We just move it into the AX register, which is what the print hex function expects, and then we call that and it'll print the hex value to the screen. And then we can just look that up online using a hex calculator or something to see what it is in decimal. And obviously we have to divide that value by the 18.2 to to get the number of seconds, but this is also something that's fairly straightforward for us to do. So once we're done, we just restore the original interrupt handler and exit to DOS. So let's save this and we'll assemble and run it and see what happens. That's just TASM timer and T-Link timer as usual, and then we're ready to run it and see what happens. So now it's installed the interrupt handler and it's counting ticks, and we can leave this run for quite some time actually and press the key whenever we want, and it'll tell us how many ticks there were before we pressed the key. So let's do that now, and it says 1 for C. So the 1 would be 256, the 4 would be another 64, and the C would be 12. Well, I don't know, you can work out what that is. Of course, we then need to divide that by 18.2 to get the approximate number of seconds. And so now we have a timer for timing our code. Now there's obviously a few ways we could improve this. One would be to print the number of ticks out in decimal, or even better, just print out the number of seconds. At the moment it's a little bit inconvenient to use. The other way that we could improve this is by having the counter do faster ticks. So for that we'd have to intercept interrupt 8 itself, and then we would just call the original DOS handler from our handler, but we'd only do that at the same rate that DOS was expecting. So for example, we could do ticks 16 times more often than they currently are, just by setting a different value in the pit counter, and then only every 16th pulse actually call the DOS handler. And so DOS would still get its pulses at 18.2 times a second. It wouldn't know any different, and we'd be able to use the faster ticks for a much better timer with better accuracy. But all of that's for a later video. This will certainly do fine for now, since we're timing things that take multiple seconds anyway. So we're all ready to start timing our code and improving it, which we'll do in the next few videos in this series.